In this lecture, I will explain what is anomalous Zeeman effect. When atoms with non-zero spin placed in a weak magnetic field, a spectral line will split into more than three lines. This phenomenon is called anomalous Zeeman effect. And if it is a very strong magnetic field, the number of lines will reduce to again 3, and that effect is called Paschen-Bach effect. Now, the important point is atoms with non-zero spin. For example, if you consider sodium atom, its atomic number is 11. Sodium 11 is has electronic configuration 1s2, 2s2, 2p6, 3s1. So there is one unpaired electron which results in a non-zero spin of half. Now, sodium atom has an orbital angular momentum and an orbital magnetic moment. Also, there is a spin angular momentum and a spin magnetic moment. So we can define the total angular momentum and total magnetic moment for sodium atom. The orbital angular momentum is given by square root L into L plus 1 h cut, where L is orbital angular momentum quantum number. It can take values 0, 1, 2, etc. And the corresponding magnetic moment is given by minus GL E by 2m into vector L, where GL is called Lagrange factor for orbital motion and its value is 1, which is obtained from experiments. Now, spin angular momentum S is equal to square root of S into S plus 1 h cut. These are the magnitude. Here S can take values half, 1, etc. If there is only one outermost electron, then S will be always half. And the spin magnetic moment mu S equal to minus Gs E by 2m into vector S, where Gs is 2 and it is known as Lagrange factor for spin motion. Now, the total angular momentum is represented as J and it is given by square root J into J plus 1 h cut, where J is total angular momentum quantum number. Its value is modulus L plus S to modulus L minus S. And mu J is minus Gj E by 2m into J, where Gj is Lagrange factor for total motion. Okay. Now, how can we find Gj? Look at the vector diagram. Here, this blue arrow represents the magnitude of orbital angular momentum and indicates the direction. So, mu L will be opposite to L and its magnitude is E by 2m times the magnitude of L. Suppose E by 2m is half, then the length of L divided by 2 will give you the length of mu L. Now, S spin angular momentum is represented by this green arrow and mu S will be opposite to that and its magnitude will be 2E by 2m times that of S. Here I assumed that E by 2m is half, so 2E by 2m is 1. So mu S and S will have the same length. L and mu L are not the same length. Mu L is only half of L, but S and mu S are of the same length. Now what happens? If you take the resultant of S and L, the parallelogram law will give you the J vector as given by this black line. The resultant of mu L and mu S is given by this solid dark line. It is the resultant of mu L and mu S, but it is not opposite to j. We defined mu j in such a way that mu j is minus gj e by 2m into j. That is, in this definition, mu j should be opposite to j. But here, the resultant of mu l and mu s is not exactly opposite to j. This is due to the fact that these constant terms are not equal. One is e by 2m and the other is 2e by 2m. If these two are equal, then the resultant of mu l and mu s will definitely opposite to j. But now the situation is different. We need magnetic moment which is opposite to j. For finding that magnetic moment, take the component of mu l along the direction of j and component of mu s along the direction of j. Add these two components, then it will give you mu j. Take the component of mu l opposite to j and component of mu s opposite to j. The sum of these two lengths will give you this mu j. So mu j is given by mu l cos lj. Mu l cos lj, that is, this angle is lj, so this angle is also lj. So mu l cos lj will give you this component. Mu s cos sj will give you this component. The sum of these two will give you mu j. But by definition, mu j is minus gj e by 2m into j. So substitute that here. Mu l I have minus gl e by 2m into l. Mu s I have minus gs e by 2m into s. E by 2m will cancel from all terms. Minus also will cancel. Then the remaining is left hand side is gj into j. Right hand side is l cos lj plus gs is 2. So 2s cos lj. Now you have to apply cosine law. Consider this triangle. This triangle. This side is s because this is s, so this will also be s. This is s, this is l, this is j. Applying triangle cosine law, s square is equal to j square plus l square minus 2lj cos of angle between l and j. Similarly, if you apply cosine law in this triangle, this side is L. So L square is j square plus s square minus 2sj cos of angle between s and j. These two are cosine laws. From the first cosine law, you can write L cos Lj as j square plus L square. This s square will come to this side, so that becomes minus s square divided by 2j. Similarly, from this equation, I can find s cos sj as s square plus j square. This L square will come to this side, minus L square divided by 2j. Substitute this s cos sj and L cos lj to this equation and add the similar terms. You will get 3j square plus s square minus L square divided by 2j square. 3j square 2j square plus j square എന്ന് എഴുതുക. 2j square plus 2j square divided by 2j square is 1. That is 1 plus j square plus s square minus L square divided by 2j square. Now we already have the magnitude of j as square root j into j plus 1 h cut square. So j square becomes square root j into j plus 1 h cut square. L square becomes L into L plus 1 h cut square. S square becomes S into S plus 1 h cut square. Substitute all these values. H cut square will cancel. So Gj will be 1 plus j into j plus 1 plus s into s plus 1 minus L into L plus 1 divided by 2j into j plus 1. So this is the equation for finding Gj. Gl, that is Landési factor for orbital motion, is 1. Gs, Landési factor for spin motion, is 2. And Landési factor for total motion is Gj equal to 1 plus j into j plus 1 plus s into s plus 1 minus l into l plus 1 divided by 2j into j plus 1. Consider the term 2s half. We want to find Gj value. 2s half means 2s plus term symbol is usually written as 2s plus 1 l j. Instead of 2s plus 1, here you have 2. So 2s plus 1 equal to 2 implies s equal to half. Now the central letter s is corresponds to capital L. If it is the letter is L, S, then L value is 0. If that letter is P, L value is 1. If that letter is D, L value is 2, and so on. So here, since that letter is S, you have L is equal to 0. J is given by this letter. J is half. So Gj is equal to 1 plus half into half plus 1 plus half into half plus 1 minus 0 into 1 divided by 2 into half plus 1. Substitute in this equation. Solving this, you will get 1 plus 1 equal to 2. So Gj value for this particular term 2s half is 2. Similarly, I can calculate Gj value for 2p half. For 2p half, s is half because 2s plus 1 is 2, so s is half. Since the letter is p, L value is 1, it is half means j is half. Substitute the equation for Gj, you will get it as 2 by 3. For 2p, 3 by 2, again s equal to half, L equal to 1, but j is 3 by 2. Substituting, you will get Gj as 4 by 3. Similarly, for any term, you can calculate Gj value. Gj value. The Dantage factor can be calculated for any term, okay, using this expression. Now, I will explain what is anomalous Zeeman effect. An atom with a non-zero spin will have both orbital as well as spin angular momentum. So, we can always define a total angular momentum J. That J vector is represented here, and corresponding magnetic momentum uj will be opposite, and its magnitude is minus Gj e by 2m into this. When you apply an external magnetic field, this J vector will precess around this B. Larmor precision we already discussed in the previous video. So, uh, due to this mu j, in presence of magnetic field, there will be a torque. That torque will be always perpendicular to j. So, that torque will always change the direction of j, and that j will eventually precess around B. That precision is called the Larmor precision. And the interaction energy is given by Gj, Mj, Bb. The derivation of this is also done in the previous video. So interaction energy is Gj, Mj, mu, Bb. In the previous video, we discussed normal Zeeman effect where spin is 0. So total angular momentum J is nothing but orbital angular momentum. Then the equation was Gl, Ml, mu, Bb. Gl is 1. So it was simply Ml, mu, Bb. Here it is Gj, Mj, mu, Bb. Now Gj is given by this expression. Mj is projection of j. It can take values from plus j to minus j. Mu b is Bohr magneton. Its value is 9.27 into 10 to the power minus 24. B is external magnetic field. Now we will consider as an example the splitting of sodium D1 and D2 lines. So what is mean by sodium D1 and D2 lines? Consider sodium atom. It has an atomic number 11. The ground electronic configuration is 1s2, 2s2, 2p6, 3s1. I can draw the diagram as 1s, 2 electrons, 1 upspin, 1 downspin, 2s, 2 electron, 1 upspin, 1 downspin, 2p, 6 electrons, all are paired, 3s has only 1 electron. So outermost you have an unpaired electron, 3p is vacant. When this electron gets some energy, it will excite, it will go to the upper state. Suppose this electron jumps from 3s to 3p, then your excited electronic configuration becomes 1s2, 2s2, 2p6, 3s0, 3p1. This s electron jumps to p. So the diagram will be like this: 3s is in vacant, 3p is filled by 1 electron. Now, according to Sommerfeld atom model, when this electron jumps back from 3p to 3s, you will get a single line. That is known as sodium D line. But when spectrometers of higher resolution were discovered, it was observed that this D line is actually a combination of two lines. They are later named as D1 and D2. And this splitting is explained using spin-orbit interaction. With the help of spin-orbit interaction, we can show that this p level will split into two. That is, a doublet will be formed. One is 2p 3 by 2, the other one is 2p half. So this 3p I can denote as 3 2p 3 by 2, 3 2p half. 3s will, in spin orbit interaction, it will remain as a singlet state and it is 3 2s half. So we can consider two transition. One is called D1, 2p half to 2s half. The other one is called D2, 2p 3 by 2 to 2s half. D1 line will have a wavelength of 5896 angstrom. D2 will have a wavelength of 5890 angstrom. The difference is just 6 angstrom. So these were observed only after the introduction of high resolution spectrometers. So spin orbit interaction helps us to explain this phenomenon. Now, what happens to this D1 and D2 lines when we introduce an external magnetic field? When we introduce an external magnetic field, you will have an interaction energy delta E equal to mj, gj, b. So there are three levels: 2s half, 2p half, 2p 3 by 2. For 2s half, we already calculated the gj value and the g factor is 2, and mj, since j is half, mj can have plus half and minus half value. So delta E will get 2 value. Mj is half, Gj is 2, half into 2 will 1, so it is mu Bb. Then Mj is minus half, Gj is again 2, so we will get minus mu Bb. Similarly, for 2p 3 by 2, Gj value we already calculated as 2 by 3. Mj can take two values, half and minus half. So delta E becomes half into 2 by 3. It is 1 by 3 mu Bb. Then minus half into 2 by 3, minus 1 by 3 mu Bb. So these are the figures. This is 2s half, this is 2p half, this is 2p 3 by 2. 2s half will split into two. One at mu bb, one at mu bb, the other at minus mu bb. 2p half will split into two. One at 1 by 3 mu bb, the other at minus 1 by 3 mu bb. Similarly, 2p 3 by 2, gj value is 4 by 3, gj value is 4 by 3, delta E is mj. For j equal to 3 by 2, mj can have values 3 by 2, 1 by 2, minus 1 by 2, minus 3 by 2. So there will be 4 interaction energy. 3 by 2 into 4 by 3, we will get 2, 2 mu bb. 1 by 2 into 4 by 3, we will get 2 by 3 mu bb. Then minus 1 by 2 into 4 by 3, minus 2 by 3 mu bb, minus 3 by 2 into 4 by 3, minus 2 mu bb. So this 2p 3 by 2 level split into 4. 2 mu bb, 2 by 3 mu bb, minus 2 by 3 mu bb, then 2 mu bb. Okay, so these are the splitting. So here I think this is drawn. This should be like this. 2 by 3 is 0.67. This is a mistake. Uh, Now these transitions are like, okay. Selection rule for the allowed transitions are delta mj is 0 plus or minus 1. So we will denote mj values here. This is mj equal to 3 by 2. And this is half minus half minus 3 by 2. Half minus half, half minus half. A transition from 3 by 2 to 1 by 2 is allowed, but 3 by 2 to minus 1 by 2 is not allowed because delta mj becomes 2. It is not allowed. 3 by 2 minus minus 1 by 2 becomes 2. That is not allowed. So from 3 by 2 you have only one transition. From 1 by 2 you can have a transition to 1 by 2 and you can have a transition to minus 1 by 2. From minus 1 by 2 you can have a transition to half, you can have a transition to minus half. From minus 3 by 2 you can have a transition to minus half only. So there are 6 possible transitions. So effectively this D2 line in presence of magnetic field will split into 6 lines. So this is with magnetic field. This is without magnetic field. Without magnetic field, the sodium has two lines D1 and D2. But with magnetic field, this D2 line will split into 6. Similarly, you can see that this half to half is allowed, half to minus half is allowed, minus half to half is allowed, minus half to minus half is allowed. So total 4 transitions. D1 line splits into 4. So effectively, the sodium D line will split into 10 lines. D1 into 4 and D2 into 6. So total 10 lines. This splitting is called anomalous Zeeman effect. In presence of a weak magnetic field, the spectral lines of atoms having non-zero spin will split into more than 3 components. It is called anomalous Zeeman effect. Thank you.